So hello everyone. Today we will be starting with Boolean algebra. So before we start, I would like to tell you most students think Boolean algebra is difficult, but it's actually very simple if you actually understand a few simple basic rules. So let me make this simple for you. So the diagram what you're seeing here is nothing but a combination of and OR gates. As you know, the output of AND gate is AB. If the input is A and B, the output will be AB. And for OR gate, the input will be B and C, so the output will become B plus C. So similarly, after all the operations, we get the output Q. So what is Boolean algebra? Boolean algebra is the mathematics behind digital electronics, which deals with the values only zeros and ones. So using Boolean algebra, we can represent and simplify logic circuits. So there are three basic operations in Boolean algebra. The three basic operations are AND operation, OR operation, and NOT operation. So in AND operation, if the output is 1, or so in AND operation, output is 1 when only when both the inputs are 1, which we can see as AB. And in OR operation, the output is 1 if at least one input is 1. The output will be in the format of A plus B. And coming to NOT operation. NOT operation just flips the input. If the input is 0, the output becomes 1, and if the output is 0, the input will be 1. Similarly, the answer will be A bar, or you can also call it as inverse of A. So moving further, we will be seeing important laws of Boolean algebra. This will help us to simplify expressions. So the first law will be identity law. So in identity law, we can see that A plus 0 is equal to A, and A dot 1 is equal to A. And coming to the second law, which is null law, and in null law we can see A plus 1 is equal to 1 and A dot 0 is equal to 0. And the third law will be idempotent law. In idempotent law, we can see A plus A remains A and A dot A remains A. So moving further, we'll be going to see De Morgan's law. So you can ask me, what is De Morgan's law? De Morgan's law basically has two major rules. The rule 1, complement of A and B is equal to A complement or B complement. So this is A and B, and this is A complement or B complement. So you can see in the diagram where A, B is given as the input for an AND gate to give output Y, which must be equal to inverse of A, B as an input to an OR gate, which gives the output Y2. So coming to the truth table, we can see the first part of the truth table with output Y denotes NAND gate. The second part denotes OR gate. So in the NAND gate part of the truth table, we know NAND gate's output remains 1 if any one input is 0. So here we can see for input AB, which is 0 0, the output remains 1. For input 0 1, the output is 1. For the input 1 0, the output is 1. And for the input 1 1, the output will be 0. And for OR gate, and in simple words, we can remember this truth table by just taking the inverse of AND gate. In AND gate, only the inputs with 1 1, the output will be 1, and the inputs with any 0 will be 0. and for OR gate we have to give the inputs as the inverse of A and B. So the zeros become 1 and 1s become 0. So the OR gate operation is basically when both the inputs are 0, the output will be 0, as you can see here. If any one input is 1 in the input stage, both the output will be 1. So as you can see here, when input is 1 1, the output will be 1. When the input is 1 0, the output will be 1. When the input is 0 1, the output will be 1. This part of block diagram, so truth table, does the OR operation. So moving forward, we can see the rule 2. Rule 2 states the complement of A or B is equal to A complement and B complement. So you can see this is the complement of A or B, which is equal to A complement and B complement. So in the truth table we can see A and B are given as an input for a NOR gate with output y1, which must be equal to inverse of A and B, which is given to AND gate with an output y2. In the second rule truth table you can see the first part of the truth table denotes NOR gate and the second part denotes AND gate. So in the first part of the truth table we can see when the input is 0 0, the output will be 1, and if there is any 1 1 in the input, the output will be 0. So this is nothing but the reverse of AND gate, OR gate. If any one input is 1, the output will be 0, as you can see here. And coming to the second part of the truth table where the inputs are inversed, so 0 becomes 1 and 1 becomes 0. This part of the truth table performs AND operation, where if both the inputs are 1, the output is 1. As you can see here, when the both inputs are 1, the output is 1. In other ways, the output is 0. So let us look at an example for De Morgan's law. So we take this equation as an example. So the first part is breaking the longest bar. So we have to break the toppest bar. So once we break the top bar, we will be left with these two equations, one on the left side, one on the right side. Apply identity. A double bar is equal to A. So wherever we see A double bar, it will be considered as A. So A double bar becomes A, and over here on the RHS side, A double bar becomes A. And by using distributive property, we separate both the equations. So A plus BC and AB bar. The A from the RHS comes to the LHS side and becomes AB bar, and the BC from the LHS side goes to the RHS side, becomes BCAB bar. So applying identity, AA is equal to A to LHS. So AA is equal to A. So this two A's will be considered as a single A in the LHS side. And applying the identity A bar is equal to 0 to B and B bar on the RHS side. So applying identity to A bar, we get the final output as AB bar. So after all the required operations, we get the final output as AB bar. So that's it for the video. So in this video we learned Boolean algebra, its basic operation, laws, De Morgan theorem, De Morgan theorem. In the next video, we will learn K-maps, which makes simplification even more easier. Follow and subscribe Silicon Mentor for more VLSI content and join our journey. Thank you.